So I thought I'd do something a bit different with the channel and kind of try to do an educational video here about binary. It's meant to kind of help people who are confused or trying to figure it out have a little clearer understanding of it. It's kind of built on the framework I came to understand binary under many years ago. It's certainly not the authoritative guide to understanding binary or deep into the details and that kind of stuff. It's just kind of meant to be a fairly high level view of binary. So let's go ahead and jump right in. So the first thing we need to discuss a bit are number bases. And by number bases, I mean the number of symbols used in that number base. Base 10 uses the digits 0, 1, 2, 3 through 9. You're all familiar with. We all work in base 10 every day. We just don't realize it. For the base 10 system, there are 10 digits. The little 10 here representing the base of the number. Normally, the convention is if you don't see a base number, it is base 10. In the base 10 system we all use every day, there is a series of symbols, and I want you to think of these as symbols, not numbers, that represent a value, a quantity. So I said the math you learned in school is base 10. When the base isn't defined, we default to base 10. So by writing 1024 here and not defining a base, we know it's really 1024, base 10, or what you think of every day as the number 1024. Binary works on base 2, and what that means is there's really only two symbols we manipulate in base 2, a 0 and a 1. So when we see 101 written this way, we know it's implied as a base 10 number. When we see 101 written this way with a little 2, we know it's a base 2 number. So we can look at this and know that this is a binary value, where this defaults to being a decimal value. So let's go ahead and dig a bit deeper into base 10. As we talked about a second ago, in base 10 we have 10 digits or symbols that are represented here. These digits are actually symbols that we have an agreed upon meaning, and in that context we look at this symbol and we say there's none, the quantity has nothing in it. When we look at this symbol, we all agree that that means there's one apple. But it's a symbol that conveys the meaning that there's one of something, and this is a symbol that conveys there's a quantity of two of something. Again, these are represented in base 10. There's no little base symbol down here. But think about these as symbols. They're simply symbols that you and I agree convey some kind of a quantity of something. We could easily use the symbols as represented right here. And if you and I agreed that this symbol meant there was zero quantity of something, this symbol meant it has one quantity, two quantity, etc., we could communicate using these symbols to represent quantities of something. So again, think about these as symbols. They just basically represent a quantity of something. So I'm trying to shift your view of seeing these as numbers to symbols that represent quantity. This will help you move through different number bases. So we just talked about the fact that we have an agreement between us about what these symbols represent. We also have a mutual understanding of how we manipulate these symbols to represent quantities. This is the math you learned in school, your normal base 10 math. That same approach to math applies in different base systems. Base 2 works mechanically the same way that base 10 does, you just have less symbols. So keep in mind that the following symbols are all expressed in base 10. So we start out representing quantities of none. This symbol means that we have no objects, we have no apples. We have another symbol that says we have one apple, and another symbol that says we have two. And as we work through the base 10 system, we get through all 10 of the symbols and we run out of symbols. So what do we do in this case? We start a new column and we start with the next symbol and we go back to the original symbol. Drawn another way, we could also, with these symbols, represent no quantity with 0, 0, with this set of symbols. And then if we had a quantity of 1 and 2 and 3 and so forth, and when we got to where we'd used all the symbols, we increment the next column and we go back to a 0. What I'm trying to get through here is that these zeros are implied typically in the base 10 system. We just don't write them out, but we know that Zero quantity of 10, zero quantity of 100, zero quantity of 1,000. We just don't write those out. Mechanism here again is exactly that. Use all the symbols, start a new column, go through all the symbols again. When this column's out of symbols, start a new column, and we work our way up. We also have an agreed upon weight for each column. Again, we all learned base 10 math in school, and we understand that in the number 1024 in base 10, that this position right here represents how many ones of an object we have, and this one here represents how many tens of an object we have, and how many hundreds, and how many thousands. So if we take the number in a column and represent it or multiply it by the weight of that column, which I'm doing over here, the weight of this column is 1,000. We know we have 1,000 in that column. We know we have no hundreds. We know we have 2 tens, and we know we have 4 ones. And if we total these up, we end up with 1,024. So again, the thing I'm trying to emphasize here is columns have weights. They represent some quantity that is then multiplied by the value here to get the total quantity that column represents. So let's kind of recap these first few slides, because these fundamentals are very important when you're thinking about numbers. We've discussed that number bases are represented. We have base 2, base 10, etc., and how by not writing in the base number right here, we all agreed that this represents a base 10 number or decimal number. We discussed thinking about these as symbols that represent some quantity, rather than thinking that as the number 1 and it means there's one object. It is a symbol. In this case, says there are 10 objects, a quantity of 10, these two symbols together. We discussed that the columns have weights. This is the number of ones in base 10. This is the number of tens quantity. And we talked a bit about how we manipulate these symbols as we count up. We add columns as we need to. So the next point I want to make here is an important one. You already know how to think in different base systems. You do math in base 10 every day, but you also work in base 12 and you work in base 60. You just may not recognize that fact. We have 12 months in a calendar year. That is a base 12 system. We have an agreed upon series of symbols to represent those months. In this case, I pick in Jan, Feb, March, October, November, December. This set of symbols represents the first month in that 12-month system. This one represents the second and the third. Again, these are just symbols that we agree upon represent a month in the 12 calendar month system. I also recognize that the symbols I've thrown out here really only apply in English-speaking countries, but it doesn't matter what the symbols are. As long as you and I have some kind of an agreed standard that what we see here represents some quantity, in this case the quantity of months, we're great. These 12 symbols could also be represented by 1, 2, 11 through 12. Whatever our standard is, we've agreed upon it and we understand it. These symbols could be a bang or an @ sign, and these symbols, again, we could agree that if you see this symbol, it's the second month of the calendar year. So if you think about this a bit further, you already think in base 24. There's 24 hours in a day. You understand how to manipulate time on either a 24 or 12-hour period. If you think about it, for a 12-hour day, if we say 2 a.m., the symbol that the 2 a.m. as a group of characters represents is a symbol that means 2 in the morning. Where if we see 2 p.m., that set of symbols there, that symbol represents 2 in the afternoon. And the same thing goes for hours and numbers in a second. The number of seconds in a minute, or the number of minutes in an hour. It's a base 60 system, and you're used to thinking about seconds as I'm going to go from 00 seconds to the symbol 59 seconds. And then I have no more to count. I'm going to go to the next column, which represents ones of minutes, and I'm going to increment it, and I'm going to start this over. It's all the same thing. It's just the agreed upon context of what the symbols mean, and that rule set that we use to manipulate those symbols. So with some of that background out of the way, let's move the conversation to binary. Why binary? Why not design a computer to use base 10? After all, that's how we think. Computers use binary because it's much easier to actually implement. Mechanically, electronically, however you're going to represent it, it's much easier to represent an on or off state. Binary only has two symbols. You hear 0 and 1 or false and true. It represents two different states of something. And that's mechanically, electronically easy to represent. My examples here, a switch is either on or off. The light bulb on that switch is either on or off. That's a binary condition. It's either on or off. It's easy to see and represent. The contacts inside of a relay are either closed or open. Relay is really just an electromagnetically driven switch. But again, we could say if the contacts are closed, it represents a 0. If they're open, it represents a 1. A voltage is either present or not present. There's 5 volts here, I'm going to call that a 1. There's 0 volts, I'm going to call it a 0. A transistor is either on or off. These binary implementations are easy to do, where something's on or it's off. It's easy to do mechanically or electronically, so it makes designing the hardware simpler. When we take this binary digit, this I can be on or off, it's described as a bit. Bit represents one binary digit that's either on or off, 0 or 1, true or false. Said another way, the bit can be in one of two states. The states are easy to detect electronically or mechanically. So again, I'm going to kind of repeat what I've said several times, because these are important things to get into your mind and think about and internalize and understand. When we discussed base 10, we talked about there being a set of rules to manipulate the symbols. These same rules apply in binary. Once we've used all the symbols, we add a new column. Each column represents a quantity. Adding up the weights of each column will give us the total quantity represented. Again, in binary, there's only two symbols. Base 10, there's 10 symbols. Binary, there's 2. So let's take a little more detailed look at binary. As we dig into binary, again, pay attention to the base of the symbol, as we'll be mixing both base 2 and base 10 numbers as we proceed. You see the little 10 here. We know that's a base 10 number, the number system we're used to dealing with every day. So we have 149 apples. This is 149 represented in base 10. And this represents, there's column weighting to it. So we know that this 9 right here is the number of 1. So 9 to the 10th, or 9 times 1 means there's 9 apples represented in that column. The 4 is the second column, and it tells us that there's 4 groups of 10 in the column, or 40. And the same thing for the hundreds. We know there's one group of 100 represented by the weight of that column being 100. And if we add the 100 to 40 to 49, we get 149. Well, in binary, we write the same value as this group of bits, base 2. The columns have values, weights, and we'll dig into that next. So, how does 149 in base 10 become this string of digits in base 2? Again, there's only 2 symbols in base 2. Once we've used each symbol in a column, we add a column here just like we did in base 10. Remember, the columns in base 10 are weighted the number of 1s, the number of 10s, the number of hundreds, again, represented in base 10. The columns in base 2, however, are weighted a little different. This first column has a weight of 1, a weight of 2, a weight of 4, a weight of 8, a weight of 16, 32, 64, and 128. When we're back in base 10, this first column has a weight of 1, and we multiply that 1 by 10 to get the weight of the next column, in this case 10. If we then take that column weight of 10 and we multiply it by 10, we get the weight of this column, or hundreds. Binary works the same way. We start with the column with the weight of 1. We then multiply that by 2 to get the weight of this column, which is 2. We multiply that column's weight to get the weight of this column, which is 4. 4 times 2 is 8. Times 2 is 16. 32, 64, and 128. So the same rules that tell us the column weight here tell us the column weight here. In binary, we're simply multiplying by 2, whereas in decimal, we're multiplying by 10. I've written this out here in several different ways, but these all kind of convey that same meaning. Columns have weights. In base 10, it's 1, 10, 100. In base 2, it's 1, 2, 4, 8. Multiplying by 10 to get across here, multiplying by 2 to get across here. couple other things here just to think about is the fact that so we were raising the powers here. It's a different way of saying the same thing. We'd have our column weight of 1. 10 to the first is 10, so we'd have a column weight of 10. 10 to the second is 100, a column weight of 100. Or, 10 times 10 is 100. Base 2, again, they're just powers of 2. 2 raised to the 0, 2 raised to the first, 2 raised to the fourth. If we get to 2 raised to the seventh, we end up with 2 times 2 times 2 times 2, 7 times to get a weight of 128 base 10. So let's look a little further into how 149 base 10 becomes 10010101 base 2. In the little graphic here, the first thing I want you to see is that these are the column weights for these binary digits. So this column right here has a base 10 weight of 1. This column here has a weight of 4 represented in base 10. This column has a weight of 16 represented in base 10. And this column a weight of 128 in base 10. So we know when we convert this binary value to base 10 that we have one weight of 128 base 10, one weight of 16, one weight of 14, and one weight of 1. And if we do the math here in base 10, we end up with 149. 149 base 10 is 10010101 base 2. It's the column weights, in this case, powers of 2. 2 times 2 is 4, times 2 is 8, times 2 is 16, on up the chain, and this, of course, can go on for hundreds of thousands of digits. Columns, if you need to. So why is binary so valuable? We talked a little bit earlier about it's easy to implement in a machine. The switch is on or off, the transistor is on or off, the relay is closed or open. It's easy to implement in physical hardware. Computers are abstraction machines, and this to me is a really key point of this. All the machine can do is turn 1s to 0s and 0s to 1s. That's all the way the computer can do. But we as human beings choose to take those groups of bit and abstract them into meaning other things. So we could take a series of binary bits and abstract them into something we can understand. So as we just saw in the last slide, this set of bits base 2 can mean 149 base 10. This same set of bits could represent how bright the green pixel on your computer screen is. If they're all zeros, it could mean there's no green. If it's all ones, it could mean we have the maximum amount of green. How we abstract this into how it is represented to us is important. These two binary patterns can represent the same thing. A binary pattern could represent a character on your screen. Here we have the pattern in binary for a capital A and a capital B, or an X or a Y. Again, it's abstraction. This group of bits could also be mixed into the group of bits here for the green's getting pretty bright, the green's getting a little brighter, the green's getting even brighter. How we choose to represent that group of bits to us is important. It's an abstraction. These groups of bits can mean anything you want them to mean. So let's take this even a bit further. Binary also is the language the CPU understands. The CPU goes out to a memory location and pulls in a group of 1 and 0s. And it might be a context, it's manipulating a number or a character. But it might also mean for the computer to do something, a computer instruction. So I've just thrown some things here. That same set of pattern that we saw a minute ago that was A, B, X, and Y could also be a machine instruction that tells the CPU to add two values or subtract or compare or, decrement a value. The context that these are used in is important. Basically, the same group of bits can mean anything the programmer wants them to represent. They can be organized into as many or few as needed. Groups of 8, 16, 32, 64, and 128 are really common groups of bits. When you hear somebody talk about vintage computing and 8-bit computing, that typically meant the computer worked with 8 bits. This width right here. In our modern era, most of us have 64-bit computers at home. So there's 8 groups of 8 bits. So this is a very wide series of 1s and 0s. That is the number of bits the CPU fetches from memory, writes to memory at a time. Again, we can, whatever width of bits we need to do the work is what we do. So another advantage why binary is so valuable in computers, it's easy to store bits. You have a magnetic hard drive in your computer, or maybe a magnetic floppy drive. A bit position on that disk can be magnetized or not. Maybe it's magnetized with the North Pole up and or the South Pole up. And those can be represented, or used to represent a 0 or a 1. So we end up with patterns of magnetic bits written across the disk that can be read as a 0 or a 1. Notice that it's an OR here. It's magnetized or not. The North Pole is up or the North Pole is down. It's an OR between them. The memory cell on the RAM, ROM, or flash memory computer has an electric charge, or it doesn't. That single cell is charged, or it's not charged. It represents 1 or 0, depending on how you want to look at it. But again, it's an OR. It's easy for that to represent a 1 or a 0. If you've ever seen a punched card, it's got a series of holes punched into it. A hole is punched or a hole is not punched. And that creates a binary OR. It's punched or not. It's a 1 or a 0. It's also easy to send bits. In the days of modems, you heard that horrible squeal on the phone line. Well, that squeal was a set of frequencies, and one set meant there was a 1, another set meant there was a 0. And it just serialized those up and sent those bits down the a phone line, the light in a fiber optic link. If the light is on, it could represent a 1. If it's off, it could represent a 0. If it's being driven at a certain frequency, it could be on a different frequency, it's a 0. Again, the OR becomes important. It's one state or the other. Simplifying this way down, if I'm standing out in an open field and I hold up a fist and tell you that means a 1, or an open hand and tell you that means a 0, I could send binary coded messages to you. The OR is what's important here. A bit is either a 1 or a 0, and it's easy to represent that 1 or 0 in many different mediums, in many different ways. So we've kind of come around full circle here. We've talked about that binary consists of groups of bits. Might be 2 bits, 8 bits, however many we mean. The position of the bit conveys a meaning, typically a quantity. This is where we looked at the first column has a bit weight of 1, the second column a bit weight of 2, the third column a bit weight of 4 when we're talking binary. It's easy to represent in actual hardware. As we said, switches on, switches off, relays closed, relays open. The same rules that you apply when you're working in base 10 apply in base 2. You can even use the same rules to add and subtract binary values. It works the same way. You just need to think about it in base 2, and if you do this a bit, it'll become obvious and simple. And you already think in different bases, 12, 60, 365, the number of days in a year. You do that, it's natural. Don't let binary be intimidating. It just takes a little bit of thought and practice, and it becomes second nature, just as base 12, base 60, base 365. It's just as easy to manipulate in your mind as these are. You just have lots of practice with these. So I thought we'd come all the way back around to this slide we looked at earlier and kind of try to talk it through again, because this gets down to the nuts and bolts of it. You've got a series of binary digits. In this case, it's 8 wide. The columns convey a weight. The weight being what quantity they represent in base 10. So we know we have a quantity here of 1 in base 10. We know we have a quantity of 4 here in base 10. We know we have a quantity of 16 in base 10. And we know we have a quantity of 128 in base 10. And of course, where those zeros, those values aren't represented. They don't have any weight. And by adding these weights together, we can represent a number in base 10. This is all, again, here represented in base 10. If you sat down and played with this a bit, you discover that you can represent every value in base 10 from 0 to 255. If all the bits were a 1, in base 10 you would add the number 128 to 64 to 32 to 16 to 8 to 4 to 2 to 1, and if you total those up, that's 255. So these 8 binary bits can represent 256 unique values in base 10 from 0 to 255. So kind of do some thinking about column weights. Think about them in base 10 as you do your normal math. You learned this in school most likely. And how by simply shifting that thinking to the column weights are different, it falls out. You know, it's the same thing, just a slightly different way of thinking because the column weights are shifted. It's also a slightly different way of thinking because you're looking at a base 2 number here. And in your head, you're somewhat converting that to a base 10 value that represents the quantity represented in base 10 we're all used to working for or with. Anyhow, I hope this made some sense. I'll be interested in some feedback. You know, if this helps one person out there get over the hump or actually get interested in sitting down and breaking out pencil and paper and playing with this, then my mission's accomplished. As I started with, it's not meant to be an authoritative guide to binary. It's not probably the best way to teach binary. I believe in alternative ways of learning. Lots of people learn different ways, and even if this didn't speak to you, it may speak to somebody else. You know, it speaks to me when I think about it this way, and hopefully it will to somebody else. Anyhow, if you got this far, thanks for listening, and we'll talk soon. Bye.